Hi, so we'll talk about another sorting algorithm, merge sort. First, we talk about how it works. So here is a summary, performance summary of all the sorting algorithms that we've studied so far. So we know for bubble sort, insertion sort, and shell sort with shell gaps, they are all n square quadratic. And for shell sort with Hippar's gaps, it is n to the 3/2 power, but even that is polynomial, and there are better sorting algorithms um, that can run faster, and that is O of n of log n, and um, merge sort is one of such algorithms. Excuse me. So, a bit of history. It was invented in 1945 by John von Neumann. If you don't know him, he's a genius. Basically, makes lots of different contributions in both theoretical and practical sciences. So, merge sort is just another of his little inventions. And yeah, he did this in 1945. And as we said earlier, sorting has been studied very well since the very, very early days of computing. So, um, the way to see how a merge sort works is, as usual, let's go through concrete examples to see what happens. So the idea of a merge sort is that if we have two sorted lists, we can merge them and merge them fairly quickly. So here are two sorted lists, right? One is slighter than the other, but so how do we bring them together? How do we merge them together? Well, so we maintain a pointer in both lists, and this pointer means that it points to the first element that has not been merged in in the in each of these lists. Okay, so when we first started, of course, the two pointer is pointing at the first element of both lists, and now we compare both 3 and 9, and we know 3 is smaller than 9, so we'll take 3, put it in the merge output, and then because we already put 3 here, we can move the pointer in the first list to the next element. Now we do not move the pointer to in the second list because, well, we haven't put 9 anywhere yet, right? So okay, now the next thing is we're going to compare 9 and 27, and 9 is smaller, so now we take 9 and put it in the merge output, and we move the pointer or the reference in the second list to the element after 9. And then we continue. We compare, we compare 10 and 27. 10 is smaller. We put 10 here and we move the pointer. And then actually, now that you've seen a few steps, can you actually pause the video and kind of try to complete the rest of the merging process? So assuming you've done that, so I'm just going to run through the rest of the process. We compare 27 and 82, put 27 here. Next one, we compare 38 and 82, put 38 here, 43 and 82, and again, put 43 here. Now at this point, we are done with the first list. That's why the pointer is kind of out there. And then we can just take whatever is left in the second list and put it at the end of the merge output. So, okay, so now that we've seen how the merging can be done, but still the question is, when we want to sort a list, we don't come with two sublists that are already sorted, right? We start with a list of totally random elements. So how do we get two sorted lists so we can merge them? Well, you might want to pause and think a little bit on your own how to do this. The answer is actually not that hard. And if you need a hint, I'll say think recursion. Okay, so here is what it is, and this is a merge sort is a fine example of why recursion is such a useful and in fact powerful techniques. Okay, so here is a pseudocode for merge sort. Right, and think about whenever we talk about recursion, there's a base case. What is the base case for merge sort, or as a matter of fact, any sort? Well, if the input list has 0 or 1 elements, then we're done, right? This is the terminating case. There's no work to be done. And then if not, then if it has 2 or more elements, then we can kind of divide the list or the iterable into 2 halves. And then we can recursively call merge sort in the first half and then merge sort on the second half. So once the merge sort is done on these 2 halves, we should have 2 sorted sublists, and then we can merge the sorted sublist, the 2 sorted sublists together using a merge function. So in terms of pseudocode, and actually even the idea itself, using recursion is very, well, I wouldn't say very, it's fairly straightforward, and it's quite elegant.